Hey Matt, all right, what I'm going to do, I'm just going to do a recording of this thing. I think you'll make some sense of it. I'm going to talk fast, so see if you can catch up. Now, these are the two formulas. I think you probably know what these things look like. I know you asked about combinations, but in order to explain combinations, I got to use permutations for it and vice versa. I think both of them kind of help each other out through explanations, which is kind of a strange way to do it. And I'm going to use an example to kind of make the most sense of it because we can actually logically apply it too. Okay. Let's start off with, I'm going to give you 5 letters here, A, B, C, D, E. Now, the reason why I have to talk about permutations as well is because in permutations, order matters. In combinations, order does not. But we got to start by talking about order mattering, because talking about this n factorial up top, what does n factorial have to do with? Well, when I have A, B, C, D, E right here, that's an element of 5 different letters, and that's what n has to do with. N is my 5 right here. So if we're asking about 5 factorial, well, 5 factorial is the number 5 times 4 times 3 times 2 times 1, but that doesn't change anything. That becomes 120. Now, what does that number represent in the situation of 5 factorial? What did I just do? 5 factorial and A, B, C, D, E, etc. tells you how many different ways that you could rearrange the letters A, B, C, D, E, meaning changing the order. So if I, just give an example here, if I have the letters A, B, C, D, E in this order, this is one way I could arrange these 5 letters. Another way I could arrange these 5 letters is by switching maybe the D and E. Keep ABC the same, switch D and E. There's another way. Okay, so I found all the different ways I could just rearrange D and E. Now let's maybe look to C. C hasn't changed yet. Maybe I put the D in its place first, and I put the C here next. Now I can swap E and C together, keep the D in the same place, and boom, that's 4 different ways. And now that the D's been here, hey, we haven't put the E in that place yet. Let's keep AB the same. Let's put E in this place and have CD. And let's go ahead and swap the D and the C. E, D, C. There. Now I've found 6 different ways I can rearrange these letters, and I haven't touched A and B at all. In fact, I've touched C, D, and E all in such a way that in the 3rd, 4th, and 5th position, these are the 6 different ways you can do it. So I started just by swapping D and E right there, and then I went ahead and saw, hey, what happens when you swap C right here, and it looks like down here when I swap just these last 3, there are 2 different ways I can swap 2 letters, but there are 6 different ways I can swap 3 letters. Now this would continue. The next letter to go here would be B. I'm not going to keep going. I'll go and put C here and just B, D, E like that. But now B comes into the mix, and now I'm looking at these 4 letters that can change suddenly. It's not just this. I'll leave A in the same place, and I'll rearrange all 4 of these letters in that kind of same fashion that I just did. So now you're looking at this and so on and so forth, and this keeps going for a while. How many times? Well, it has to do with factorial. Starting with the red right here, this is just the number 2 factorial. This is 2 times 1, which is 2. 2 different ways I can rearrange that. The green right here, that's 3 factorial. That's 3 times 2 times 1, which was your 6. So how many different ways could I arrange 4 letters here, starting with moving that B around and doing that? How many different ways could I do for purple? That would be 4 factorial. That would be 4 times 3 times 2 times 1, which is 24 different ways. Again, I'm not going to do it. And when A comes into the mix and I have to rearrange it with all of those, that's where we get back to 5 factorial, and that's where you get 120. So that's what the n factorial has to do with. They first ask you how many different ways can you rearrange the order of all your letters here. And let's not call them letters. Let's call them first names of, let's say it's a basketball pickup game, and you're reordering the positions. There's Albert, there's Bob, there's Charlie, David, and Eric, and he's playing point guard right now, shooting guard, small forward, power forward, and center, but then I could rearrange them in different ways, where he's the point guard for a long time, and then you see all the different arrangements. Maybe he's not as good, but that's not the point of the question. Okay, so that's the part with the 5 factorial right there. Now, K has to do with this next set here, where we're saying, what if we don't look at just all 5 numbers? And you could choose all 5 right here, but what if instead we wanted to limit ourselves, not instead of having all 5, but limit ourselves to, say, 3. I have 3 spots open. Maybe it's a pickup game. I have a nice big roster of all these people here, but now in a pickup game, I can only have 3 people, and I need to select, I could do A, B, C, but I could also do C, E, D, and I could do B, E, A, just whatever else. There are a lot of different ways I could rearrange those. And that's where these questions come in. I limit the number of things that I have, and does order matter or does order not matter, which is going to be a big question. Okay, So to make best sense of this, I'm going to kind of use what I was talking about right here to do it, because I did limit myself to 3 people. You might ask, how many different ways can I rearrange 3 people? You can only rearrange 3 people 6 different ways, okay? But we're not limiting ourselves to 3 different people to choose from. So when we talk about something like a permutation right here, the reason why that n minus k factorial comes into play, when we're doing a 5 pick 3 scenario right here, that's 5 factorial over 5 minus 3 factorial like that, which is 5 factorial over 2 factorial. Okay, what does the 2 factorial have to do with? It has to do with the fact that we are dividing out sets of combination or sets of arrangements that we are not choosing in our number of, like how many different ways. Remember, this question was how many different ways can you arrange 5 people if order matters. This is how many different ways you can arrange 3 people if order matters, keeping in mind that 2 are, say, on the bench. Okay, even though there's a guard, a forward, and a center that's in your 3-on-3 game, there are 2 that are on the bench right here. So how many different ways can I arrange just 3 people with order mattering? Based on this green, I shouldn't use the red right there. Based on this green right here, these 3 that I rearranged, that answer is 6. So there are 6 different ways to arrange 3 people. So is that the answer to 5 pick 3 though? Let's check it out. So we have 5 factorial over 2 factorial. Now that's going to be 120 divided by 2. Now that's 60. So something's a little different here. How come this answer is 6 and this answer is 60? Because you have to consider the fact that I was only looking at arranging C, D, E. What if B comes in the game and plays with D and E? What if A comes in the game and plays with D and E, etc.? The next question that I can also ask myself here, and this is kind of where combinations happen. The next question I got to ask myself here is, how many different ways can I just arrange, excuse me, how many different ways can I just arrange 3 letters out of the 5 that we have right here, order not mattering, meaning if A, C, and E all play together, doesn't matter what position they play right now, I just want to know how many different ways that I can rearrange those things. And that's where this formula comes into play right here. And I know I'm explaining one by explaining the other here, but basically, let's try and find, and I promise you this number is not huge, but how many different ways can I just arrange these letters here in sets of 3 with order not mattering? I can do ABC, I can do ABD, ABE. Okay, now I've exhausted all the different ways A and B can play together. I can do ACD, ACE, and I can do ADE. Now I've exhausted all the different ways that A can play. Now I can do BCD, BCE, BDE, and there should be one more than and CDE. All right, so there are 10 different ways that I can rearrange these guys right here to play together, okay? Just in the sense that, okay, you guys can play, or no, now you guys can play, whatever. So that's 10 different ways of doing substitutions, okay? Now, you have to consider that within these 10 different ways, you can rearrange their positions 6 different ways. That's what we talked about right up here. Right up here, I can rearrange them 6 different ways within. So within the CDE lineup, C can play guard, then D here, etc., or you can swap forward and center right here, etc. So within these 10, the 6 different ways there. So there's the 6, where is it? There's the 6 here, and there's the 10 here. These two guys kind of got to multiply together right now. Okay, these two guys got to multiply together because we're saying how many different ways can I substitute these guys in, and then how many different ways can I rearrange them within if order matters. That's why we're doing 60 as 10 times 6 right there. And that's where that number kind of comes from. So again, the 2 just says adios to these guys when it comes to rearranging, but they can still sub in, and there are, oh, by the way, 10 different ways to do that. So that kind of explains away the permutation formula in itself, and the combination formula just has one more facet to it, and it's kind of the part that I just talked about last here. It was saying how many different ways can you sub these guys with order not mattering. So if we have the 60 as that answer to start right here for the permutation, the combination has an extra factor of dividing by k factorial. Well, k factorial, hang on, this is messy, I know. 5, choose 3 right here. This is going to be 5 factorial over that 2 factorial there. times this k factorial, this 3 factorial right here. We know that 5 factorial over 2 factorial is 60, so we still got to divide by that 3 factorial. 3 factorial is 3 times 2, which is 6. What is the 6? It's ignoring the order that matters portion. We do not want to rearrange the people here. We don't want order, we don't want order to be mattering in this particular case now. So we got to divide out all the different ways we can rearrange the people once they're in the lineup. That's what gets me down to just these guys right here. And it just says, okay, so all I got to do within is just not rearrange them. Or, like that part doesn't matter. The mom is saying, hey, as long as little Bobby's playing in the game, that's all I care about. I don't care if he's guard, forward, or center. So, it's like that kind of thing. And Bobby can play in any of these games, looks like right here, any of these 6 different ways. So, anyway, in that way, I'm dividing out my ways that I'm rearranging it afterward. And that's what that extra portion's doing right there. It's taking out the rearrangement factor. The 3 factorial saying, hey, they're subbed in, but don't rearrange them now. Because I don't care about that instance. And then the permutation phase says, yeah, we do want to shuffle them still. So that extra factor right there, that's got to be included in my set. That was the multiplication by 6 kind of thing, or by 10 in this case here. So anyway, that's a very small explanation there. I don't want to play proof with it. I just want to play example because I think logic makes more sense. And I know basketball. So that's just kind of the gist behind it. One small thing, it's kind of cool. If you're not very good at the formula, I don't know if you've seen Pascal's triangle before. It looks like this, and I can't spend forever talking about it. Pascal's triangle has a lot of different neat things involved in it. If you don't know what I'm doing right now, you might be able to pick up the pattern very quickly. I didn't memorize this thing. What I'm doing is I'm adding 2 numbers together to make another number within, like this right here. You can see how these numbers are adding to make these other ones, okay? Pascal's triangle, like I said, it has a lot of different things to it, and the ones kind of stay on the outside. But one other thing that Pascal's triangle does have to it, and this goes on forever, by the way. One thing that Pascal's triangle does have to it is it does use the sense of combinations in kind of a neat facet. Pretend like the first row is called row 0, and then the next one is row 1 and row 2. Remember, row 0 has 1, row 1 has 2, row 2 has 3, etc. Row 3, row 4, and row 5. Within these right here, if you don't have a quick way of calculating your combination stuff, you can probably use a calculator in what you're doing. But if you wanted to pique your interest here, 1 is also 0, choose 0. And then in my row 1, 1 is also 1, choose 0, and 1, choose 1 for that one. This one is 2, choose 0, 2 is 2, choose 1, and 1 is 2, choose 2. And then so on. I'm only going to write one more. In row 3, I have 3, choose 0 here, 3, choose 1, 3, choose 2, and 3, choose 3 right there. This keeps going in this way, and it's always symmetric, by the way. You can tell when it divides in. Once you pass the middle number right here, it goes back down to its thing. So if I did add another row here, this is 1, 6, 15, 21, and then 15, 6, 1 again. It goes back down. Because once you have more people to choose from there, then it's less ways that you can kind of do rearrangements, things like that. All right, anyway, so that's just that gist there. Hopefully that was helpful. I know this is kind of a longer video now that I talked about it, but it's kind of a cool facet there. I know you asked about it. I want to help you, so hope you enjoy this thing. Peace out, Girl Scout.